Hello and welcome back to hansonmath.com tutorial videos. Today's lesson is on a conic section known as the ellipse. Before we get to the ellipse, let's look at the cone, which is where all of the conic sections come from. This is a single cone, and right now we're putting horizontal slices through it. That is, slices that are parallel to the base, and you'll notice that we have circular cross sections. The closer you are to the base, the larger the diameter, and the closer you are to the vertex or the summit, the smaller the diameter. Now, you'll see here that we're starting to move away from the cross sections parallel to the base. Now we're looking at cross sections that are oblique or on a slant. And you no longer have a circle, now you have an oval shape, which is the ellipse. So this is the new conic section that we're looking at, an ellipse, which is an oval-like shape gotten by slicing a cone at an angle. Now, the textbook says that the ellipse is the set of all points in a plane such that the sum of the distances from any point P to two fixed points, F1 and F2, which are called the foci, is constant. Well, let's take a look at what that means. Okay, now you'll see that there is a point that's tracing around the elliptical track here. And you'll see that this point here is called a focus, or one of the foci, and so is this point here. So that you could call that F1 and F2. Now, you notice that as this point traces around, the blue line gets bigger and smaller depending on how close the point around the curve is to the foci, and same with the red line. And you'll notice that as you go around the curve, the length of the blue line and the red line change, but what remains constant is their sum. So no matter where you are, the sum of the length of the blue line plus the red line is 10. Now, it's 10 in this case just due to the scale and the size of this ellipse. That 10 will change. That doesn't remain constant from problem to problem. But what will remain constant and what makes this thing an ellipse is how that no matter where you are on the curve, the sum of the blue line plus the red line will always be constant no matter where you are.
Shape that you get when you slice a cone. And what's interesting about it, the ellipse has two focus points with a geometrical property that's been known for 2,000 years, that if you put a ball on one focus point, in whichever direction you hit it, over here, over here, over here, over here, every single point that it hits, it will rebound into the pocket.
Okay, there was a real life application for you guys. Just keep in mind that this only works with an elliptical shaped pool table. What they showed you doesn't hold true with a rectangular shape. Okay, now we will move on into the main portion of our lesson after that brief introduction. We've been through the definition of an ellipse. I have this printed on your note paper, which you can download. And if we move along here, let's work on one together where we're going to plot some points and establish an ellipse, and then we will learn stuff about it as we go. Okay, so you can do this with paper and pencil. If you don't have a printer, you can just do, a y-axis and an x-axis with the little marks like that on paper. That'll take care of it just fine. For the sake of me doing this in this format, it's a little bit less messy if I have the printed graph paper. All right, so let's plot our four boundary points. So we have -3, 2, which is right here. We have 7, 2. We have 2, 5. And we have 2, -1. Okay, and that will establish our oval curve, which is our ellipse. Okay, now Let's answer some questions about some particular features of the ellipse. The orientation of this one is called horizontal, and the reason it's horizontal is because it is wider than it is tall. And we'll get to something called the major axis in just a moment, but whichever way is the bigger way is the orientation. So this one's horizontal because it's wider. The center is right smack dab in the middle of the thing. So we can see visually that the center is right here. So its coordinates would be over to, up to, or to. The vertices are the endpoints along the bigger way. So this is the wider dimension of the ellipse. So the vertices would be, let's see, -3, 2. And this one here is 7, 2. Okay. The co-vertices are the endpoints of the shorter axis through the ellipse. So that would be specifically this one. That would be a co-vertex, which is at, I could call that CV. That would be a 2, 5. And its buddy would be right here, which is 2, -1. The major axis length, that's the distance through the ellipse. Think of it as a diameter, but it's not a diameter because the diameter is for a circle, and now we're dealing with the ellipse. But the major axis length is all the way through the long ways. So let's see, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the major axis length is 10. The minor axis, as you can probably guess, is the shorter way through. So that would be 1, 2, 3, 4, 5, 6. And that brings us to writing the equation. How do you write an equation of an ellipse? Well, it works like the following. First, you have the center, which is x, and then it's the opposite sign of these coordinates. So it's x -2 parentheses squared plus y opposite coordinate -2 parentheses squared. Now you have a diameter, or you have a denominator, and that's gotten by the following. Along the x horizontal way, because remember x is horizontal, the distance from the center to this vertex, this is called A, the bigger way. Okay, so that's A. So this is 1, 2, 3, 4, 5. But this component right here is A squared. So 5 squared is 25. Okay, A was 5. Now, this component here along the minor way, just halfway from the center to the co-vertice, that's called B. And this component or denominator of the equation is B squared. So let's see, what do we have here? 1, 2, 3, that was 3. So 3 squared is 9. And then a standard aspect of the equation of an ellipse is it's always equal to 1. That's a constant. And there you have it. So the equation of this ellipse is as follows. Now, there's something known as the foci. Those are those special focal points that we saw in the example with the pool table, and also with that interactive example with the track. How you find that is given by an equation, c squared equals a squared minus b squared. So we have c squared equals a squared and b squared are these denominators. So it's 25 minus 9. So that's to say that c squared equals 25 minus 9 is 16. You take the square root of both sides. The square root of 16 is 4. And that's the distance from the center to each foci. And the foci always lie on the major axis, or the bigger way. So if we start at the center here, I'm going to count 1, 2, 3, 4. So that's one foci, or one focal point. We could call it F1. And then from the center, I can go the other way, 1, 2, 3, 4, and we'll call that F2. Okay? Now, if we want their coordinates, the coordinates of these foci would be, in this example, it would be 6, 2. And the one towards the left would be -2, 2. Okay? Finally, the last thing that we're going to add in that, if you study this in Algebra 2, you may not have gotten to is something called the eccentricity. The eccentricity is a measure of how oval or how elliptical the shape is. You're always going to get a value between 0 and 1. If you get a value closer to 0, it's more circular. And if you get a value closer to 1, it's more oval. It's gotten by the formula. The eccentricity is equal to the C value divided by the A value. So the C value was 4, and the A value was, if A squared was 25, then A would be 5. So it's 4/5, which is 0.8. Okay, 0.8 is closer to 1 than it is 0, so this one is more on the oval end of the spectrum. All right, now we're going to move into a couple of examples, and we'll keep it moving. Here you will see from the textbook the standard equation of an ellipse, as we just talked about. The A squared value is always the bigger component. So if A squared is attached to the X fraction, it's going to be horizontal. And if the A squared is attached to the Y fraction, it's going to be vertical, or taller than it is wide. Of course, if you're centered at the origin, you won't have this H or K shift value, which is fine. Okay, so here's some more particulars, and without further ado, we'll get right into a couple of examples. So, graph. Starting with example 1. How do you graph this one? Well, there's no parentheses, there's no shift on the X and Y, so that tells us something important. That tells us that our center is at the origin, or 0, 0. Okay, so we'll plot our nice center. And like I said, the bigger number is A squared, the bigger denominator. The smaller one is B squared. So if A squared is 25, that would imply that A is 5, because you'd have to take the square root. So since that's attached to the Y fraction, Y stuff goes up and down. So from here I go up 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5. And then I take the B squared, which is 16. I take the square root of that. The square root of 16 is 4. That's with the X fraction, so that's horizontal movement. So from the center, I go horizontally 1, 2, 3, 4. And the other way, 1, 2, 3, 4. Those are my endpoints of my ellipse, which define my major and minor axis. So now I can make my sketch. And the only thing else I'm going to do is I'm going to put in those foci points, which are gotten by C squared equals A squared minus B squared. So I have C squared equals, remember, A squared and B squared are my denominators. So they are 25 and 16. So it's C squared equals 25 minus 16, which is to say C squared equals 25 minus 16 is 9. Take the square root of both sides, and C equals 3. So I start from the center and I go towards the major way. So this one is taller than it is wide. So from here I go up 1, 2, 3. So that's one focal point, and down 1, 2, 3. That's the other one. Okay. This is my center. We could call that C. And this is one vertex, and this is the other vertex. Okay, we'll move on now to example 2. We always want to start with the center. So the center here is going to be HK, which is the opposite. The H is the opposite of what you see after the X. So that would be -1. And the K is the opposite of what you see after the Y. So that would be +5. So I have a center at left 1, up 5. And now I need to use the denominators to establish my widths, if you will. So I have a denominator here of 36, but where's my denominator over here? Well, if you don't see one, just like with any fraction, you may put over 1. So my bigger one is a squared. The smaller denominator is b squared. So now I have a is the square root of 36 is 6. B, the square root of 1 is still 1. So notice that the bigger denominator, a squared, that's attached to the x fraction. So x is horizontal. So that means from here I go horizontally or over 6. 1, 2, 3, 4, 5, 6. And also from that center point to the left, 1, 2, 3, 4, 5, 6. And then my b value was 1. That was attached to the y. So that's vertical. So that's up 1, down 1. You'll notice that this is a very, very skinny ellipse. And you can imagine that the eccentricity would be closer to 1 because it's more oval in nature. Now, the only thing else I'd like to put in is those focal points, the foci. So again, that's c squared equals a squared minus b squared. So we have c squared equals, that was 36 minus 1. So we have c squared equals to 35. So we'd have c equals the square root of 35. Now, the square root of 35, that does not help me conceptualize where to put this on the graph. So I know it's close to 6 because the square root of 36 is 6. The square root of 35 is 5.9, which is just a whisker short of 6. So from my center, I can't go up and down because I'd go outside of the curve. You have to stay on the major axis. So from here, it's 1, 2, 3, 4, 5. It's as close as you can get to the end. And then 1, 2, 3, 4, 5.9, it would be right about there. So that's one focus and the other focus. This is a vertex. That's a vertex. That's your center. Remember, you can hit pause, you can rewind, make this video work for you. Do what you need to do to succeed. In example 3, we're going to look at starting with a general conic form of an ellipse where it's not apparent where's the center, where is the a squared, where is the b squared, there's no fractions, it's not clear. So what we need to do is we need to convert this into the standard form of an ellipse so that we can make some sense out of it. And to do that, we're going to use an old technique called completing the square that you might remember from Algebra 2. So to begin to do that, what you want to do is you want to organize this starting with the x squared term. So we have 9x squared, and then we have the other x term, which is a minus 54x. And then now we'll organize it by the y term. So we have a positive 4y squared. We have plus 40y. I'm going to put the equal sign next, and we're going to take the constant and we're going to move it over, which would be like subtracting 37 to both sides. So you'll have negative 37 over here if you subtract it to both sides. The next thing we're going to do is we're going to do an organizational step where we're going to take this 9 here, which is the coefficient on the x squared, and we're going to factor it out. So we factored it away from the x squared. So that means we also have to factor it out of the 54. So if you divide 9 out of 54, you're left with 6. And then we're going to leave a placeholder, which I call an empty box. This is part of the process known as completing the square. Now, let's do the same process for the y terms. So on our y squared, its coefficient is 4. So if you pull that out, you have 4 parentheses y squared plus you divided the 4 out. So if you divide 4 out of 40, that leaves you with 10y plus this placeholder, and that equals negative 37. Okay, now the question is, what are we going to put inside of this placeholder box? Well, to complete the square, what you do is you take half of the x coefficient and then you square it. So half of negative 6 is negative 3, and then negative 3 squared, negative 3 times itself is 9. But whatever you do to one side of the equation, you have to do to the other. So we have this 9, but it's also being magnified by the 9 we pulled out. So we have 9 times 9. And then how do you get this box here? Well, same deal. You take half of the y coefficient. Half of 10 is 5. 5 squared is 25. And then you also have to add that on over here. So it's 4 times the 25. Okay. Next step is to simplify a little bit. So we have our 9. And now we're going to take this trinomial and we're going to switch it to its binomial squared alter ego or nickname. So you have x and then you have minus, and you can either take half of this or the square root of that. It's the same thing. Half of 6 is 3. So I encourage you to work this on paper. If you do x minus 3 times x minus 3 and FOIL it out, you'll get right back to this, I promise. Okay, plus we have our 4 here. We've got, this is going to be our y binomial squared. You take half of the plus 10, which is plus 5. I promise you, if you take y plus 5 quantity squared and you work it out, you'll get right back to this, equals negative 37 plus 81 plus 100. Okay, so let's see. If you take your calculator, negative 37 plus 81 plus 100, you get 144. So actually, I'm going to erase this, and I'm just going to put 144. Now, how do we make this look more like the standard form of an ellipse? I want a 1 here. I don't want 144. How do I get a 1? Well, I divide it by itself. That'll give me a 1. But whatever you do to one side of the equation, you have to do to the other. So I have to divide everything by 144. Now, essentially, we're pretty much wrapped up here, but we have to simplify a little bit. We have to do 9 into 144. 9 goes into itself once. It goes into 144. Let's see, 144 divided by 9 is 16. Okay, that canceled. So now we have x minus 3 squared at the top, plus, let's see, 4 will go into itself. 4 goes into 144 36 times. We've got, that was y plus 5 quantity squared equals 1. Okay, so there you have it. That is the standard form of the equation of an ellipse. The bigger denominator is always a squared. The smaller one is b squared. I'm going to attempt to move the screen up right now and we'll graph it. And, you know, we've got everything right at the tip of our fingers now to graph it and find out the particulars. Okay, so now let's see what we know about this ellipse. We can figure out the center, I think, pretty fast. Center would be HK, which is the opposite of what you see here. Opposite of negative 3 is 3. And the opposite of the positive 5 is negative 5. So let's see, we go over 3, down 5. There is your center. Now what else can we do? We can get the endpoints, right? So if we take the square root of 16, that would be b is equal to 4. And if we take the square root of 36, that would be a is 6. So remember, this a is 6. This is attached to the y. Y is vertical. So from here, I go up 1, 2, 3, 4, 5, 6. I go down 1, 2, 3, 4, 5, 6. So I'm off the grid a little bit. So those would be the vertices. So our vertices are 3, 1 and 3, negative 11, I believe. All right, we can put in the co-vertices. That would be given by this length here of 4. That would be the x-way, which is horizontal. 1, 2, 3, 4. 1, 2, 3, 4. Now I can graph in our elliptical path. Something like that. Don't judge me here. Looks kind of like a kidney or something. Now what do we need to find? We got the center, we got the vertices, we need the foci. The foci is gotten again by c squared equals a squared minus b squared, where those are your denominators. So that would be 36 minus 16. All right, so c squared would be 36 minus 16 is 20. Take the square root of both sides. So c is the square root of 20, or you could break it up with a perfect square. It's root 4 times root 5, which would be 2 root 5. Now, 2 root 5, I don't really conceptualize that distance. So if I do 2 root 5 or root 20 into my calculator, we get 4.5-ish. So now I can conceptualize that. 4.5 would be 1, 2, 3, 4 and a half vertically from the center of the ellipse, and then 1, 2, 3, 4.5 vertically from the center of the ellipse. Now, why vertically? Well, that was because y was the major way, because it has the larger denominator. The last thing here is we'll figure out the eccentricity. The eccentricity is c divided by a. Our c was the square root of 20. A was 6. So we'll put that into the trusty old calculator. The square root of 20 divided by 6, easy for me to do, is 0.75. All right. At this point, I would encourage you to hit pause and try the next example on your own. So you may want to pause your screen right now and hack away at number 17 here. See if you can replicate the same process. If not, you can release pause at any time and we will work through it together. All right, so without further ado, I'm going to start to organize this again, as soon as I can bring up my pen. First, I'm going to group together the x stuff, which would be 6x squared plus 18x. Next, I'm going to group the y stuff, which would be plus 2y squared minus 10y. And then I'm going to take the constant and I'm going to, do the opposite. So instead of plus 2, I'm going to minus 2. When I do that to both sides, I would get negative 2. All right. Next, we're going to get ready to complete the square. So you take the x squared coefficient. In this example, it's 6. You factor it out. So now you have 6 to the quantity of x squared plus, you have to factor the 6 out of the 18. 6 goes into 18 3 times, plus our constant placeholder. Now, same deal with the y squared. You factor out the, what happened to my pen? Factor out the coefficient of 2. So you have 2 times the quantity of y squared minus, you factor 2 out of 10, you get 5, plus our placeholder constant equals negative 2. Now let's work on completing the square to get the box value. Now this one's going to come out a little bit messy. We take half of 3, which is 3 halves. Okay, so think about 3 halves. And then we're going to square it. 3 halves squared, you'd square the top and bottom, so you're going to get 9/4. And now when we add that for balance on the other side, it's 6 times the 9/4. So I'm going to do 6 times 9/4. Okay, and then when we do the completing the square over here, I have half of -5, so that's -5/2 squared, which would be positive 25 over 4. But to balance it out, it's being magnified by this 2, so it's going to be 2 times 25 over 4. Okay, the next step is to transition this into a binomial square. So I have x plus, again, half of the 3 is 3/2, plus my 2 times my y, binomial square. So again, I have half of this -5, which is -5/2. And now I have to simplify all of this stuff. So let's see. I have a -2. I have 6 times 9/4. That would be 54/4, which is 13.5. And then I have, let's see, 2 times 25 is 50. 50 divided by 4 is 12.5. 13.5 and 12.5, what is that? 26 plus -2 is 24. So now I need to get my 1 instead of 24. So I divide it by itself, and I divide by 24 everywhere to balance it out. Now I will simplify, and we will be well on our way here. 6 goes into itself, 6 goes into 24 4 times. Let me recopy my numerator. Right? Plus 2 goes into itself, 2 goes into 24 12 times. Let me copy the numerator. And 24 24 is 1. Okay, so now we've got the standard form of the ellipse. It's not pretty, but we know a lot of things about it. And let me clear off some of the screen, and we'll graph it and take this one home. Okay, so what do we know about this ellipse? We know the center is at the opposite of this, so that would be a -3/2. And the opposite of -5/2 is 5/2. So we'll plot the center. -3/2 is -1.5, and then 5/2 is 2.5. So we're about right there. That's our center. Okay, I'll put a little C for center. Now we'll work on our A and B value. Remember that the bigger denominator, which here is 12, has to be A squared. The smaller one has to be B squared. So then we know that if B squared is 4, just regular B is 2, which would be half of the minor axis. And if A squared is 12, then A would be the square root of 12, which another way to think of that is it's divisible by the perfect square 4. So that's √4 times √3, or 2 √3. Or in terms of a decimal, the square root of 12 is about 3.5. Okay, so since this is the y fraction, this is a vertical ellipse, the major axis is vertical, so I can go up 3.5 from here. Let me change colors. Let's see. This is not going to cooperate. Change colors. Okay, I'm going to go up 1, 2, 3.5. So I am 1, 2, 3. I'm right there. I'm going to go down 1, 2, 3.5 right here. 1, 2, yep. So those are my vertices. I'll put V1 and V2. Okay, let me change colors again. Now we'll do the co-vertices. So the B value was 2. So that would be 1, 2 to the left because we're in the X or the horizontal way, and 2 to the right. Those are my co-vertices. Now we can sketch in the ellipse if we want. Something, whoa, this is real bad. Something like that. See, what else do we need? We need we really should be writing down the location of these vertices. So let's see. Vertices, what do we have here? We have -1.5, so that's -3/2. And what is that, 6? And -3/2 and -1. Okay, how about the foci? Well, you're probably getting used to it by now. That is c squared equals a squared minus b squared. C squared equals a squared minus b squared. So we have c squared equals, let's see, 12 minus 4, which would mean c squared would be equal to 8. Take the square root of both sides. C equals √8, which is √4 times √2, which is 2√2. Then approximately as a decimal, 2√2 or √8 is 2.8. So just shy of 3. So if I go almost 3 units from the center vertically, because that's the way the major axis goes, I'd go 1, 2, let's see, not quite 3, 1, 2. So it's real close. That's one of the focal points. And then 1, 2, not quite 3. There's the other one. Okay. So if I want to write out the coordinates of the foci, I would have, let's see, -3/2, and then the center was at 5/2, and from that 5/2, I go up and down, or plus and minus, this √8 distance, which simplified is 2√2. So that would be the best way to express the foci without getting too messy. So you're at -3/2, comma, 5/2 plus or minus, which is up or down, that length of 2.2, which was at 2.8 that I tried to rough in. All right, great. For our last two examples, we're going to take a look at writing the equation of an ellipse, given a couple of facts about it. So we have to do some detective work. So the first thing I like to do is I like to make a really quick makeshift X and Y axis, and I'd like to plot, because I'm a visual person, what we're told. So the vertices, which are the endpoints of the major axis, are at 0, 8, which would be somewhere up here, and 0, -8, which would be somewhere down there. Well, what good does that do? Well, due to the symmetry here, I know that the center must be at the origin, and this distance here, halfway through, is always called your, well, if it's on the path of the vertices, that's your A. So our A length is 8, which implies that A squared is 64. That's important because that will be the denominator of our Y term. I know it's the Y term because it's a vertical axis. And now we'll put in the foci information. The foci are at 0 plus or minus 4. So I've got one of them here and one of them there. Now, the usefulness of that is as follows. The length from the focus to the center, that's your C value. So this length here is 4, which implies that C squared is 16. So now we have C squared, A squared. We just need to find B squared, which is given by the relationship here, C squared equals A squared minus B squared. We plug in what we know. C squared is worth 16. A squared is worth 64. B squared, we don't know. We want to get B squared by itself. Subtract 64 to both sides. 16 minus 64 is -48. Those cancel. That equals to -b squared. Divide both sides by a -1, and you get 48 equals b squared. And I'm going to stop there because normally I know you're really itching to take the square root, but no, that's exactly what we want. We want b squared. So now to write the equation, well, we know that the center is at the origin, so there's no shift. that would just be x squared and y squared. We know that the thing has to equal to 1 because that's the standard form. Now for our denominators, the a squared is vertical. That was 64, so that goes under the y because of vertical. And the b squared was 48. There you have it. That is the equation of this one using some detective work. That brings us to our last example, which is more of the same. Again, we need to write an equation based on what we're given, which doesn't look like much, but it goes a long way. Make a little makeshift graph. And let's put in what they tell us. Well, now they have the foci, which is at plus or minus 2, 0. So that would be 2 to the right and 2 to the left. Now, what does that tell us? That implies that the center is halfway in between. So again, the center is at the origin. And this is our C length. So C would be 2, which implies that C squared is 4. Well, what else did they tell us? They told us that the major axis has a length of 12. The major axis goes the same way as the foci do. So if the entire thing is 12, that means that half is 6. So you've got 1, 2, 3, 4, 5, 6. That's the endpoint of the major axis. And 1, 2, 3, 4, 5, 6. That's the other endpoint of the major axis. So this distance here is 6. And since that's the major way, that's your A way. So if 6 is A, then that would imply that A squared is 36. So now we've got A squared is 36. We've got C squared is 4. So now again, we can find B squared by plugging in. So we've got 4 is equal to 36 minus B squared. Subtract 36 to both sides. So you get negative 32 is equal to negative B squared, which implies that 32 is B squared. So now we'll stop there because that's everything we need. So let's think about it. This ellipse is centered at the origin. So again, no shift, no H and K. Now we just need our denominators. This one is horizontal because that's the way that the major axis and the foci all align. So our A squared is horizontal, or X, so that's your 36. And the Y squared, that's your B squared, which is 32. And we are done. Thank you very much. I hope you enjoyed this video. I hope it helps, and now you can do a little bit of work with the ellipse. Thank you very much and have a great day.